Okay, so the family of derivatives or families of curves with the same derivative. Now, let's say, for example, we had a derivative that was dy dx equal to 2x. So that is, whatever function we have, our derivative is 2x. Okay, so to get back to our original function, y, okay, well, we'd say, okay, so if we were to differentiate the original function to get an x, okay, we have to subtract 1 from the power. So if the derivative is 1, then going backwards, our derivative becomes a 2, okay? But when we differentiate, okay, so, if we differentiate x squared, okay, we put the 2 out the front like that, okay, or we multiply it by 2. So to go in the reverse order, we must then divide everything by 2. And what this is going to do is it's going to give us our derivative, which is x squared. And we can test this because we know x squared, that the derivative of that is, the 2 comes down the front and we get 2, and we subtract 1 from power and we get the x, okay? So it's a cool little trick that we've got there. The problem is, though, that this is not the only function that has 2x as its derivative, okay? For example, we could have a different function. So let's have a different function, such as x squared minus 5, for example. If I was to differentiate this, we get fx is equal to 2x, and then the 5 disappears. So it also has the derivative 2x. If I have, for example, x squared plus 3, okay, and I differentiate that, okay, we also get 2x. So the thing is that everything that has a derivative of 2x, well, the x term is still going to be x squared, but there's going to be a constant number that always appears on the end, okay? So if we only know what the derivative is, we don't actually know if there is a constant on the end or not. So what we do is we say, well, the original function is x squared plus some constant c, okay? Because we're not sure if there is a constant sitting there or not, so we're going to give it a name c, okay? Now, that's what happens when we have the x squared function, okay? So if we have 2x, we go to x squared. We can generalize this quite a bit. So dy dx, let's say it's equal to 1, then we know that the original function must have been equal to x, okay? Because if we differentiate x, we get a constant. But it's not just any x, it's an x plus some constant value. Okay, so for example, if I've got a derivative of 1, okay, then my function could be x plus 2, or x plus 5, or x minus 3. Okay, continuing this trend, if dy dx is equal to x, then our function could be in the family where x squared over 2 plus c, some constant, okay? And we can continue this pattern along, and what you'll notice is that we get kind of this pattern, okay? And this pattern is basically all we need to know about having to go backwards for our derivative, okay? And so on. You can see what's happening, okay? So these are our family of derivatives, okay? So plus the c's on as well, because there could be constant there. So each of these is a family for a different function, okay? So the derivatives, the only thing is changing, because if we're adding a number on the end of a function, all it's doing is moving it up and down based on what it is. Okay, so all of these are the same function, okay, but just moving up and down in some different way. So the derivatives, okay, going backwards, remember we're going to add a power to these ones and then just divide it by what that power is, okay? Now the reason we're going to do this is so that we can then go backwards or work backwards for any of our potential derivatives. So let's have a look at this example here. Use the table below, okay, so the table on the other side, I will say, to find the family of curves whose derivative is. So we'll start with the first one, which is dy dx is equal to 25x to the power 4 minus 3. So the reason I originally said that we're going to rewrite our derivatives as sort of like a product of the two, like this, is so that we can more or less work backwards, okay? So we don't know what the reverse process of 25x to the power of 4 is, but we do know what x to the power of 4 is. And we know that x to the power of 4 is going to turn into, so following this pattern along, so if I was to continue this pattern, so dy dx is equal to x to the power of 4, then y must be x to the power of 5 over 5 plus some constant, okay? So this first bit here, okay, so the 25 times x to the power of 4, well, it's going to change to 25 times x to the power of 5 over 5. Okay, just like that. Now we've got a constant term, and it says here our constant term. Well, I could rewrite our constant term like minus 3 times 1. So our constant term 1, okay, over on this side here, over this side here, okay, and it's x plus some constant c, okay. So again, there should be some plus c here, and then I rewrite this as minus 3 times, now it's x plus some constant c there. Now we're just going to put this together, so it's going to be 25 x to the power of 5 on 5 minus 3x. And then plus c and plus c technically make plus 2c, but like it's just a constant value. It doesn't actually, like it doesn't really matter what that constant value is, okay? Remembering we're just using the c as sort of a placeholder for some number. So even though it is plus c, it's still just some constant value that we're adding on the end, okay? We don't know what that number is, we don't know what the original c's are, but we can just put it on the end and just sort of say as a placeholder, this is a number there's going to be a number that sits here. Okay, and then just simplifying that one step further, we're going to get 5x to the power of 5 minus 3x, and then plus that constant. Okay, so that is the original function from the first derivative that we had, so 25x to the power of 4 minus 3. Okay, and we can check that. So we can check that by differentiating it. So if y is equal to that, then dy dx is equal to 25x to the power of 4 minus 3. Okay, and perfect, that's what we had to begin with. So let's try our second one. So we've got dy dx is equal to, now it's going to be 6 times x squared plus 3 times x. Okay, so just breaking the basically the scalar from the x. Okay, so y is equal to 6 times, now the derivative of x squared, the original function from x squared is x3 cubed on 3. Remember, it's some plus c, but we can just add that on the end. Okay, then we get 3 times our x becomes x squared over 2, and then also some plus c on the end, so some c that we're going to add on. So putting this together, we're going to get 6x cubed on 3 plus 3x squared on 2 plus c. So y is equal to, and that's going to be 3x cubed plus, is it 3? No, it should be 2, not 3. That's a lie. 2x cubed plus 3 on 2x squared plus c. And again, to check this one to make sure we've got the answer, we can differentiate it. Okay, so to check, we're going to differentiate. So dy dx of that is going to be 6x plus 2 lots of 3 on 2 x, and the c is going to disappear, and that just simplifies down to 6, that should be squared, x squared, and that 2 and that 2 cancels out, so we get the plus 3x. Just what we started with, so awesome. So that's how we go back in reverse, so you're basically just using those values there. You'll get the hang of these as we go on and on, okay, so you know, it is pretty straightforward, you know, whatever the power becomes, we're just going to put it over that original one, okay? So the general, we won't worry about the general form so much, but that's pretty much how we do it. Okay, with that being said, that's going to be the last of this little series of videos, okay? And we will then start the chain rule next week. Okay, so enjoy.